Hey, we're working through the 1998 AP Calculus AB multiple choice portion. So this is non-calculator, number 1. What is the x-coordinate of the point of inflection on the graph of y is equal to 1/3 x cubed plus 5x squared plus 24? So point of inflection comes from the second derivative function. So we're going to have to find our way to our y double prime. So we're going to apply power rule twice. Power rule the first time, we get 1/3 times 3 x squared plus 10x. Find the derivative a second time, and we get 2x plus 10. So the steps to find points of inflection, we're going to be taking our second derivative function, set equal to 0, find critical values, and then plot them onto our sign line. We're going to test values in each interval within the sign line, and then confirm that there is a sign change in order for there to be a point of inflection. Okay, so y double prime is equal to 2x plus 10. We set y double prime equal to 0. We solve for x. We get x is equal to -5. So that is our critical point. Now, this is something that we have to be careful about. Just because you find a critical point doesn't mean that it's always going to be a point of inflection. For this problem, it does work out, but just be careful that you have to put it onto the sign line, and you have to test values in each interval into the second derivative function, and test to see whether there's a change in sign. So if I plug -7 in, I get -4. That's negative, so I know this interval is concave down. If I plug 0 in for x, I get positive, which is concave up. Concave down followed by concave up. We know that there must be a point of inflection at x equals -5. Now, if there wasn't a change in sign, then this would be a critical point, but it would not. We cannot conclude that it is a point of inflection. Okay, number 2, we have a graph of a piecewise linear function. What is the value of the definite integral from -1 to 4? So definite integral from -1 to 4, we're going to be using the area between the graph and the x-axis. But with definite integrals, we have to keep in mind that anything above the x-axis are going to remain as positive values, but the region below the x-axis, we have to account for them being negative. So we're going to still find the area, either 1/2 base times height for triangles or width times height for rectangles, but the regions below the x-axis, we have to make sure we adjust and have those as negative values. So we have a triangle, rectangle, triangle, triangle, and square. Okay, so through these formulas, triangle being 1/2 base times height, rectangle being just width times height or base times height. We find the values, and then we just total them up. So the definite integral from -1 to 4 will be 1 plus 2 plus 1 minus 1/2 minus 1, which is 2.5. All right, for number 3, we're having to evaluate the definite integral, but just make sure that we don't skip any steps. These bounds do not see the integrand. We have to apply the appropriate antiderivative rule first, and then we can plug in the upper and lower bound. So if we look at this problem here, this is a pretty straightforward problem, but we have to use power rule, but to use power rule, we have to bring this variable has to be sitting at the numerator. So we bring that variable in the denominator up, becomes x to the -2. We apply power rule, add 1 to the exponent divided by that new exponent. So x to -1 over -1, which cleans up to be -1 over x. Now we can plug in the upper and lower bound. So the half bracket indicates that I'm going to be plugging in and evaluating my values in the upper and lower bound. So upper bound's value gets plugged in first. We get -1/2 minus parentheses, then the lower bound, which is a -1 over 1. So the two negatives become positive. -1/2 plus 1 is 1/2. Okay, number 4. A function is continuous between a and b, and differentiable between A and B. So continuous, no breaks in the graph, differentiable, smooth curve. Which of the following could be false? Okay. So I just sketched the graph just to have a visual. I created a graph where I have endpoints identified between A and B, endpoints identified and defined, and then I just connected the graph. I made the graph continuous and differentiable. And let's see which of these could be false, which means that 4 of these always have to be true. Okay, so the first statement, f prime of c is equal to f of b minus f of a over b minus a. Now, we need to be able to recognize that this is the formula for mean value theorem. This is saying that can we, whatever the slope is, whatever the average slope is between the endpoints, we can set that equal to the slope of the function and find the value where that slope exists on the curve. So mean value theorem does apply, because if it's smooth and continuous, then any endpoint, whatever the slope between endpoints, there must be that slope that exists on that graph. Okay, mean value theorem holds true. For part B, f prime of c is equal to 0. Can we guarantee a slope of 0? Now, Rolle's theorem is a subset of mean value theorem. Now, with Rolle's theorem, if we want to guarantee a slope of 0, the endpoints have to be guaranteed to be sitting at the same y value. But the problem doesn't indicate any, doesn't give us any indication that is the case. So we can't guarantee that this is necessarily going to be true. And just by the way I drew the graph, there is no places where slope is 0. So we can't guarantee slope of 0 unless the endpoints have the same y value and continuous and differentiable. Okay. Function has a minimum value between a and b. That is true. Function is continuous and differentiable, and it connects at the endpoint. So there must be a point where it's the lowest over the entire region. There's also an absolute maximum, so that's just applying extreme value theorem. And the definite integral also holds. We can find the definite integral from a to b because the graph is connected. So whatever this region is, we can total them up, and first fundamental theorem of calculus holds true. All right, so number 5, we have a definite integral here. So first thing we do is we have to evaluate the antiderivative, and then we plug in the bounds. So the integral of sine is going to be negative cosine. So once we evaluate the antiderivative, or find the antiderivative, we're going to plug in our upper and lower bound. Upper bound gets plugged in first, in for our t, so negative cosine of x, minus, then plug in the lower bound, 0 in for t, we get negative cosine of 0. Negative cosine of 0 is going to be negative 1. The two negatives become positive, so we get negative cosine of x plus 1, or 1 minus cosine of x.